Okay, so here's what we got today. We're going to finish that lab with the periodic trends, and then that's going to lead into the next set of trends. Yes.
So I have a question with the graph that we're doing for that.
Yeah.
You said to label it 1 through 10 for the atomic mass.
No, 1 through 20.
1 through 20, that's what I meant. But they go much higher than.
But yeah, no.
Only
Just
do the 1 through 20
only
ones?
1 through 20.
Okay.
Because you'll see that trend by that point.
Also,
Yes.
for like the atomic number 12, the like boiling point and melting point are like really high, like way higher than 2,800.
That's what on there it says. Don't do 12.
It just says 6.
It should have said 12.
That's 6.
Okay. Yeah. I think they were talking about atomic number, and what you have listed is mass number. I think that was the disconnect.
Okay.
So there is, on that, I don't think there is even one with 6 on there, is there? Yeah, so it's atomic number 6, but it's mass number 12. Because that's carbon. So, okay. So, if you look at, again, this perspective, and in terms of what they knew and what they didn't know. So, one of the things about certain elements is that they react very easily. And oxygen is one of those that's most famous for that. So if you look at, the wrong one, hold on. So this is representing oxygen. So, and these are like hydrogens, fluorines, whatever, anything that can give up an electron. So, if you look at this in terms of that ratio, so you can make like a little Mickey Mouse molecule, right? So this is water. So what they found, so if you look at what we now understand the periodic table. So if you look at oxygen O, that combines with 2 hydrogens, right? And so that's what that's reflective of. Oh, oxygen, and on that chart, when it says how does it react with hydrogen, it'll say like 0.5, 1, 1.5, something like that, because that was that ratio. So when you look at the element underneath oxygen, which is sulfur, okay, so sulfur has the same number of outer shell electrons that oxygen did. So sulfur reacts in the same ratio with hydrogen as oxygen did. So, but again, this was done in the late 1800s. They had no knowledge of S sublevels and P sublevels, electrons and protons and neutrons or anything like that. The only thing they could know is, well, how do these things react? So if you look at like water, for example, oh, okay, oxygen reacts with 2 hydrogens. Now, this is carbon, all right? Well, carbon actually has 4 areas that it can bond. So if carbon reacts with hydrogen, then you get something like this, which is CH4, okay? And later on we'll get into why it bonds like it does and why you have these specific angles. So this is methane gas. It has 1 carbon and 4 hydrogens. So what they did is they were able to, without knowing the structure, what they were able to do is look at, well, how do these atoms combine in a certain ratio, okay? And even that was methodically very tough to do. So what they would have to do, like let's say for example, you want to look at the reaction between hydrogen and oxygen. Well, that's tough to do because you can't watch individual atoms react. So what they would do is they would have, okay, let's say that you have a known volume of gas of hydrogen and a known volume of oxygen, and then you would see those react, and you would say, okay, well, how much hydrogen was produced, or how much hydrogen was used up, and how much oxygen was used up? What's a good ratio? And they would say, oh, that figured out that, oh, it took twice as much hydrogen as it did for 1 of oxygen. And they said, oh, that's how that got that formula of H2O. And one of the things you'll see and I'm just gonna lay this groundwork now, we'll talk more about this later, is that when you look at how they figured out these ratios were not based upon mass. So when you see the formula H2O, don't look at that and go, oh, that means there's 2 grams of oxygen to every 1 gram of 2 grams of hydrogen to every 1 gram of oxygen, okay? When you look at a chemical formula, it is a ratio of 2 things, and 2 things only. It is a ratio of atoms, and it is a ratio of moles. It is not a ratio of mass, okay? And this will play out large later on, okay? I'm just beginning to tell you this right now. When you look at the chemical formula, it is not a ratio of mass. Ratio of moles, ratio of parts, not a ratio of mass. So the other element that they reacted it with a lot was chlorine, okay? Because chlorine is very reactive and it's relatively abundant. So if you look at what they chose on this periodic table, and this is what they said, okay, well, let's look at hydrogen. Hydrogen is the most abundant element in the universe. And it's easy to generate hydrogen, okay? Take water, put some electricity through it, you can collect the gas, you're gonna get hydrogen, and you're gonna get oxygen. So it's relatively simple to generate pure hydrogen gas and pure oxygen gas. Run some electricity through it, you can do it. Or run electricity through water. You can even take a battery and do it. It doesn't take anything like, it isn't like you have to have this thing hooked up to a nuclear reactor or something, okay? Literally, very simple to split hydrogen and oxygen apart from water molecules. So then, okay, hey, here's things that we can work with. It was easy to work with chlorine, okay? Because it's pretty easy to generate elemental chlorine gas. Now the problem is, physically working with chlorine gas, number one, it's green, and it smells horrible. And it's also, because it's so reactive, it's actually very poisonous. So when the people were working with this, they had to be very careful, because if you ever inhale chlorine, that chlorine atoms would look to react with something, and if you ingested it into your lungs, the chlorine would go, oh, hey, we're going to react with the lining of your lungs, okay? Which just doesn't end well, because you can't fix that damage. But that's also, if you've ever been around a pool, this is why they use, a lot of times pools will smell like chlorine, okay? So chlorine damages your hair if you've ever swam a lot, and you know what I'm talking about, okay? So then what happens is that chlorine is very good at destroying the bacteria or organisms that live in the water, but it's also then very bad for your hair, because it's still going to react with that. So the reason that we don't use like any of the noble gases, helium, neon, argon, that type of thing, to disinfect pools, is because they don't react with anything. They're just there. It's like, okay, cool, right? You put them in with water, they're going to go, yeah, we're good. And later on we'll talk about why they're good. It's because they have a stable electron structure. So if you look at those properties that you have listed, 2 of those are what we call physical properties: boiling point, melting point. Some of them are very, very high. Some of them are very, very low. So riddle me this: the ones that have very, very, very low melting point and boiling points, are those going to be gases or solids at room temperature? Miles. If it has a very, very low boiling point, at room temperature, are those going to be gases or solids?
Solids. Gases.
Because we're going to be above that boiling. So like, let's say that you have a boiling point of, no, nobody has theirs. You have yours. Let me see yours. So like you have an atomic mass of 16, and that has a boiling point of negative 183 degrees Celsius. Okay, so that's the boiling point. So if that's the boiling point, above that temperature, you're going to be as a gas. Okay, so this would be a situation where that's a gas. Now, if you look at what allows us to be here having this conversation, if the universe didn't have gases, okay, if everything was just solids, we wouldn't be here having this conversation. Because if you didn't have the existence of gases, we wouldn't have an atmosphere, okay? We wouldn't be able to breathe in. So if everything in the universe existed as solids, we wouldn't be here. If everything in the universe existed as gases, we wouldn't be here having this conversation. Okay? If everything existed as liquids, we wouldn't be here having this conversation. So because the universe has this mix of solids and liquids and gases, so what's the most important liquid that exists on Earth that allows us to be here? Water. Okay? Think about this. What if the boiling point of water was, say, 20 degrees Celsius instead of 100 degrees Celsius? Gets pretty warm. Guess what? What would swimming pools, lakes, what would all that water do? Okay, it'd begin to boil. Okay, literally, you would see it boil. Okay, what if the freezing point of water was 20 degrees Celsius? Instead of 0, what if the freezing point of water was 20? Everybody goes, oh, that'd be cool. We'd have a lot more snow days, right? So instead of getting down to like 0, 20 Celsius, only have to get down to 20. It's like, oh, it would be snow. That'd be great. Okay. Well, guess what? All of Canada, all of North America, pretty much from the Dakotas, probably north, would be covered in glaciers. Okay, because it would be existing as snow all the time. Okay, so if you look at how we exist, it's pretty cool. The chemicals that we have the ranges that we do. Because if you think about your existence, most of what you deal with are solids. Okay, the only really gases that you interact with are your atmosphere, which is kind of cool. Liquids, you actually, if you think about it, you don't deal with a lot of liquids other than like water-based things, okay? But most of the things that exist in the universe are solid. But if everything was solid, we wouldn't be here. If everything was gases, we wouldn't be here. If everything was liquids, we wouldn't be here. So the fact that we're here is because you have a balance of solids, liquids, and gases. Okay, so the hardest part probably is to think through is going to be the graph that you have to do on the back, okay? And so with this one, come on, here's your graph. So this one, let me give you a hint. This one over here is going to be boiling point or melting point. So that's going to go from 0 to, or negative 300 up to like 2800 or something like that, okay? Let me give you a hint. On that one, you just have to make every little square be 100. So you got to go negative 300, negative 200, negative 100, on up. It's going to go to 0, and then you're going to start going positive, okay? And I don't care which one you do, melting point or boiling point, doesn't make any difference. Now, over here, this one is going to be, and I don't care which one you do. You can either do your chlorides or you can do your hydrogens, okay? That's going to be a little bit easier because like your hydrogens go from like 0 to 0.5 to 1.5 to 1 to 1.5 to 2, 2.5, okay? So on your chlorides, just go from 1 to 2 to 3 to 4, okay, and then actually come back down. So what you should see is that your melting point and boiling points, you really won't see a trend with those, okay? It's kind of going to be all over the place. The ones with the either the hydrogens or the chlorides, that one you will actually see a trend, okay? So now what you want to look at on this is because this actually this is something that Abby asked about. So that you're going to have to think a little bit. Okay, yes, I said the T word. So down here, you actually need to plot atomic number, okay, through 20. What they're giving you is the mass number, okay? So on your cards, okay, you have mass number. What you need is the atomic number. So basically, like for example, that hydrogen, and this is why if you have this arrangement correct, so basically, spin that camera around. So you're going to have hydrogen, which is going to be 1. And then you're going to have helium, and this is going to, because here's the disconnect. The information you have on those little cards is mass number. What you need to plot on that graph is atomic number, okay? So so here's hydrogen, well that's the same 1 and 1. So this one that has relative atomic mass of 4, oh, that's going to have the atomic number of 2 because that's helium. So over here, when you look at this, like here's lithium, oh, mass number 7. So they gave you the mass number, but so then you can look at this and go, oh, that's lithium, that has a mass number of about 7, so that has an atomic number of 3. So if you look at what you have, you're going to have your alkali metals here, okay? You're going to have some of your noble gases here. You're going to have some of these halogens here, and then you're going to have a smattering of ones in between. So, and again, if you're Mendeleev, you had to leave gaps because they didn't know all the elements that existed, and that's the beauty of what he did. Is that he left gaps. He goes, you know, we haven't found these elements yet, but I think they exist. So when you lay this out, look at this in terms of groupings. So over here, and this chart also, if you look at this, this has, and this is kind of color coded, so it'll tell you, oh, the blacks are solid at 25, the blues are liquid, greens are gases. And that's going to be the color of these symbols. So if you want to come up here and use this as a reference, you can and go, oh, okay, right. So notice that up here, nitrogen, oxygen, fluorine, all of these elements here and these noble gases, if you look at this entire periodic table, you have a small number of particles or atoms that are gases at room temperature. Okay, it's a very small number. You even have a smaller number that are blue, that are liquids at room temperature. So at liquids at room temperature, basically you have mercury and you have bromine. That's about it. As far as existing as elemental forms, you got mercury, you got bromine. Those are the only ones as elements that are liquids at room temperature. You notice the vast number of elements that exist on the periodic table are all solids, okay? So all of these in the S, the D block, all of these are solids. You got few gases, only a small number of that are liquids. So when you group these, come up here and go, wow, okay, I'm going to notice that all of these gases are all kind of up here in this far right-hand column. You don't have any gases over here, okay? You have no gases over here. You don't get gases until you get way over here on this right-hand side. So when you're grouping them, pay attention to that. Oh, I need to put all the gases together because that's where they all hang out, is over here. So notice that all of these, okay, like for example, here's your boiling points of like nitrogen and things like that. Those are very, 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 very small numbers because of the fact that that's why they're existing as gases at room temperatures. Whereas these metals here, those have very, very high melting points, which is why they're solids at room temperature. Okay, so to figure out, let's just from this background. So when you go to do this plot, what I did personally is that when I was making up my answer key for this, just to make it simpler, even though you have the atomic mass listed on those little cards, I went in and wrote beside that, oh, what's the atomic number of these elements? Because that made it easier to grab. And that's why it says on here, somewhere it says on there about the one with atomic number 6 doesn't fit. Somewhere on there it says that. Oh, down here. Plot the data from the elements, do not include data from the elements with atomic number 6, which is carbon. So that's why you've got to have the atomic numbers and not the mass number, and that's why it's going to go through 20. Okay, so on the graph, you're going to have, make sure I know which ones you have plotted. Did you plot boiling point and or melting point? You're just going to pick one, I don't care which one, and that's going to go on this axis. And then over here, you're going to have either the oxygens, or excuse me, either the hydrogens or the chlorines. I don't care which one that you have, pick one, okay? But you've got to figure out the atomic numbers to do this. So, when you get to, on this front page, where it says, list the 4 patterns found on the periodic arrangement, okay? Should be 4. One of them that you should see, now that you have enough knowledge of the atomic structure, let me give you a hint. One of them is that you're going to have like, oh, you're going to have the elements with S sublevels being filled, where you just have one of those. That's going to be in one arrangement. When you get over to the halogens, the fluorine, chlorine, bromine, iodine, all of those are going to be filling like the P sublevel. So we know that now. We know, oh, this makes sense, okay? At the time, we didn't know why there were 2 columns over there on the far left side. That was cool, there was 2 columns. We didn't really know why, but there's 2 columns. Then they said, oh, there's an S sublevel. Oh, that holds 2 electrons. Ah, now we know why there's 2 columns. The other big revelation came with the P sublevels, okay, on that far right-hand side. Ah, there's 6 columns. How cool is that? Wow, the P sublevel holds 6 electrons. And then it all came together. They're all going, oh, that makes sense now. This is kind of cool. And they said, wait for it. Oh, there's the D sublevel. That has 10 electrons. That's why there's 10 elements in that D block, okay? So it isn't like they said, oh, we know about S, P, D, and F. Let's arrange the periodic table. They said, let's arrange the periodic table, and later on they said, oh, now that's why it makes sense, okay? So that was kind of the big revelation. So on those 4, you can talk about melting point, you can talk about boiling point, you can talk about how it bonds with hydrogens, you can talk about how it bonds with chlorines. There's a whole bunch of different things. You can talk about, oh, it's by atomic mass. So those are the things that you want to look for when you do that. Now, when you get to the questions on the graph, okay, there's 4 questions back here that you have to answer. So, when you get to this 4th question, based upon your developed table, where will the element with the mass of 72 belong? When you get to that one, don't look at boiling point or melting point, because those are kind of all over the place. Look at either maybe like how it's going to bond with chlorines, look at how it's going to bond with hydrogens, where that's going to be, okay? So just keep in mind when you answer that. Okay, so I'm done. So go back, finish up that, get your graphs done. Remember, you're going to do atomic number, not mass number, okay? All right, stop that for a second. Okay, so let me explain these 2 pieces of paper that are on your table. It should have been saved when the copy was done. So what this is just a continuation of this idea that the table is arranged based upon certain trends, okay? So the heart and soul of this is what's happening on the back of page 1 where you have this chart, okay? It doesn't list all the elements, but it lists the main ones. So, on this chart, let me explain what each of these numbers are. So you have the atomic number, that's pretty self-explanatory, okay? You have the elemental symbol, pretty self-explanatory. You have the electron shell diagram. Oh, okay, hydrogen, wow. And it doesn't put the dots on there to show the number of electrons, but hydrogen would have 1, helium would have 2. So, notice that as you go across, as it goes across, like you get down here to lithium, oh, that starts with 2 shells. You start with sodium, oh, that has 3. You go down to potassium, that has 4, okay? So they don't show you the number, because this is like the Bohr model. They just didn't put the dots that showed the number of electrons. Now, here's the 3 things that this sheet is going to ask you about. It asks about atomic radius, and that is in PM, and PM stands for picometers, which is a very, very, very small measurement. Now, here's the problem when you talk about atomic radius, is trying to physically measure this thing. So, if I want to measure by the radius of the ball, oh, here's the center, and I have a defined outer edge. It's a physical barrier, okay? The problem with trying to measure atomic radius of an atom is that, yes, you do have a nucleus, and you only have like an electron cloud around it. So it isn't like there's a physical line. So when we talk about atomic radius, it's extremely difficult to measure. Because, you know, if you all remember, you know, if this thickness of aluminum foil, there's about 94,000 aluminum atoms stacked side by side by side, and then trying to figure out the radius of just one of those, let alone, you know, count 94,000. So it's extremely technical in terms of how you get this measurement. So the atomic radius is just the distance from the center of the nucleus out to the edge of the electron cloud. So what you see is a trend. If you go to like lithium across to neon, notice that that atomic radius starts really big, and then that atomic radius becomes smaller, because this goes back to Coulombic forces. So what happens is, as you go across, you're putting more and more protons in the nucleus, and each of those, you have more and more protons pulling on those electrons, so you have like more attractive force on each electron, so that's why as you go across, that atomic radius becomes smaller. It's somewhat counterintuitive. You would think, oh, as you go across and you put more electrons in there, electron cloud should get bigger because you're putting more electrons in there. But what's happening is as you go across, you're increasing the atomic, that attraction on an atomic level between the protons and the electrons. That's pretty straightforward. Now, the second from the bottom, this first ionization energy. So first ionization energy, here's the easiest way to think of first ionization energy, is how much energy it takes to remove an electron, okay? So here's a good analogy. So let's say Miles really likes M&Ms, okay? So he's got a small bag of M&Ms, and he really likes those M&Ms. So if I go up and try and take that from him, he's going to go, whoa, big man, back off, okay? I'll fight you for it, okay? I really like these M&Ms. Well, so do I. So if I'm going to take them away from Miles, I got to put a lot of energy in it because of the fact that he has a very strong attraction for that. Now, Grace, on the other hand, could, you know, she kind of likes him but really doesn't. It's like, okay, hey, whatever. So if I go up to Grace and go, hey, Grace, can I have your M&Ms? Yeah, I don't care, okay? Since Grace doesn't have much attraction for those M&Ms, it doesn't take very much energy for me to take them away. So what first ionization energy tells you is basically an indirect way of measuring how much attractive force there is that that nucleus holds for those electrons. So what you'll notice as you go across, that first ionization energy gets bigger and bigger and bigger and bigger and bigger. So what that means is those the outer shell electrons are held more tightly. So as first ionization energy goes up, that's a reflection of how much that electron is held by that nucleus. So think of that in terms of candy. Oh, if I really like candy, that means someone's got to take a lot of energy to take that away. Now, here, the strangest of all of these is this bottom column called electronegativity. So here's a short version of electronegativity. Electronegativity is kind of what I refer to as like the Robin Hood trend. So the Robin Hood trend, electronegativity, is the measure of the willingness of an atom to take an electron from another atom to form a bond, okay? So if you go across, you'll notice that your noble gases, helium, neon, argon, okay, they don't have an electronegativity number. They're the noble gases. They don't need to take electrons from anything, okay? So that's why those have no electronegativity, because they're snobs. They're going, I don't need you guys. I was like, I've got my own M&Ms. I don't need to take any M&Ms from any of you. That's why there's no electronegativity for the noble gases. But what you'll notice is that the halogens, fluorine, chlorine, bromine, notice that those have extremely high electronegativities. Reason that those are so high is because they have 7 electrons, and if they get one more, then they become like the noble gases. So those are very, very high numbers. The other extreme, the lithium, the sodium, potassium, those are relatively small electronegativity values, mainly because of the fact that it's like, oh, if I get an electron, great. If I don't, hey, not a big deal either. Okay? So basically, your electronegativity is a measure of a willingness of an atom to form a bond with something else by taking in an electron. So, with that said, these questions, I'd like for you to try and get through these as much as you can. It looks daunting, but most of these are really, 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 really simple, okay? Literally, I did this last night. It took me like 10 minutes, okay? So, for tomorrow, here's what I want done. I want the periodic trends, that worksheet done. If you need to take your graph with you to finish that, take that. I'd like this to be done, and then tomorrow we've got a lab on this continuing trends thing tomorrow. So tomorrow, we're going to go lab. I'll answer any questions that you have on this. It's actually pretty straightforward. A lot of times it's going to talk about Coulombic attractions. Remember, there's 2 things that affect Coulombic attractions: the number of charged particles and the distance. More charged particles, stronger force; bigger distance, weaker force. If you keep that in mind, that allows you to answer about half the questions. Okay? All right, I'm done.